Okay, folks. Okay, folks. We're a couple minutes early, but there are just a couple of administrative things I want to go over before we get into the content. In particular, I just want to remind people that on the course site, if you could please by Monday fill out your lab partner preferences, it would be a big help to me. This will take you to a Google form where you can ask to be lab partners with a specific set of people, or alternatively ask to be assigned to a lab group, and I'd be happy to do that. But in any case, if you could all please do this by Monday. The other thing I just wanted to point out is a handful of you asked if I could put lecture slides somewhere public. There's another link here now called lecture slides. If you go to this, this contains the slides. There won't always be slides for a lecture. Sometimes we'll just be looking at code, but if there are slides for a given lecture, then I'll put them here. Okay. Any questions from anyone before I get into stuff? Okay, then I'll remind you what we've been doing. For Lab 1 and for every one of your other labs, I'll remind you that you are given a demonstration project from which to start. That is to say, you are given some project that does something, and you'll modify that project in order to meet the requirements of the lab. For your week 2 checkout for Lab 1, that many of you have already gotten that demo project running. It's the beep boop example. You get it running and you plug in speakers and it goes beep boop, beep boop. Next week, what you'll be asked to do is modify that such that instead of producing pure tones, beeps and boops, it'll produce cricket chirps. And I'll just gently remind people that for this week only, folks are totally encouraged to just show up to lab, and there's a procedure to follow, and you click through the procedure and you'll be out of there. Starting next week, it's different than that. Starting next week, you're given an objective. The objective for next week is make a cricket sound. You have to design the solution to that. So I'm just gently reminding you that if you were to wait until you got to lab to look at the objective, come up with a design solution, prototype it and debug it, you're probably not going to finish in time. And if you do finish in time, you're going to be stressed, and it's not going to be that fun of an experience, which is a bummer. So please, before you come to the next lab section, read through the objective for that lab section and come up with an idea. In particular, what you'll have to come up with for the cricket chirp, we'll talk about this in the next couple of labs, is a state machine, a modified version of the state machine that exists in the demo code that produces a chirp instead of just pure tones. Well, the chirps are pure tones, but modulates the frequency, the amplitude such that it creates cricket chirps as opposed to just beeps and boops. Okay, so what I want to do today is, as I mentioned last time, for Lab 1 only, there's a repository on the course demo, in the course demo repository called Lab 1 Incremental, that incrementally adds complexity until we get to the demonstration from which you'll start next week. And this is in part to help you so that I'm not just dumping a relatively complicated example on you, and in part to help me because it allows for me to introduce these topics one at a time, to layer complexity incrementally. So I want to continue that process today. Last time we talked about Blinky, which is, it's the thing everyone does with a new microcontroller, is get an LED to blink. So that's what this example did, was get an LED to blink. And today I want to add just a little bit of complexity to that. In particular, I want to talk about the timer peripheral that's available on the RP2040. I want to talk about how to set up timer interrupts, an interrupt service routine attached to that timer peripheral. And I want to talk about the SPI peripheral. And I'm going to do so by talking through this next demo. And the way that I'll do this is very similar to last time, where I'd like to talk through the code, and when we encounter a line of the code that requires some sort of justification or explanation, we'll hop into the documentation to see why that line of code is what it is. And I'll say too that as the semester goes on, I'll do less of this, where we're sort of looking at code, then going to documentation and back and forth. Part of what I'm trying to get you all used to in the beginning of this class is how to investigate this code and how to go through the documentation. Because each of the data sheet's hundreds of pages, the CSDK guide is hundreds of pages. It can be a little daunting, right, to figure out how exactly to use those resources. And people do it different ways, incidentally. So let me just say that the way that I like to consume the technical documentation for a new microcontroller is usually the first chapter or two in the data sheet for that microcontroller contains something like a system overview, describes the system as a whole, the stuff that's available in there. I definitely read that. And usually the first chapter or two of the SDK guide explains the architecture of that SDK at a high level, and I definitely read that. Beyond that, I don't generally sit down and just start reading from front to back. Maybe some people do that. I've never met any of those people. That's not usually how people use these sorts of resources. What I like to do instead is look in that first chapter and say, okay, there's all this interesting stuff in here. There's timers and SPI peripherals and so on and so forth. And there's a chapter associated with each of those things in the data sheet and a chapter associated with each of those things in the SDK guide. So I'll then hallucinate some project that will require that I need to figure out how timers work and the SPI channel works. And then I'll go to those chapters and read those chapters thoroughly and implement this project that forced me to understand these two things. And then I'll add another peripheral. So I consume the documentation sort of piecemeal, where I read this part and then I read the chapters that are relevant to what I'm working on at that moment. And then I keep adding complexity to the projects until I've, learned a bit about each of the peripherals, or at least as many as is necessary for whatever I'm doing. And sometimes they couple, right? So for instance, maybe you want to learn about the timers because you want to set up a timer interrupt service routine. So you read the timers chapter, and then you say, oh, I should learn a little bit about how interrupts work on this system too. So you go read the interrupt chapter. But that's how I recommend approaching all this documentation, is sort of like that. Okay, so what does this example do? All that this example does, I'm going to talk through each line, but in short, what it's doing is it's setting up an SPI channel that communicates with an external DAC. The DAC being the device that many of you, except for the Friday folks, will do it this afternoon, but many of you set up the connections between the Raspberry Pi Pico and a DAC already in lab. The DAC stands digital to analog converter, so a device that you send it digital information and it converts that to an analog voltage for communication to something like a speaker, for instance. So we set up an SPI channel to communicate with a DAC, and then we set up a timer interrupt that interrupts at precisely 40 kilohertz, 40,000 times a second. And every time we enter that interrupt service routine, we send a new SPI transaction to the DAC that's converted to an analog voltage, which ultimately goes out to a speaker. And the consequence being that a pure tone comes out of the speaker, which goes beep, okay, forever. And the algorithm that we're using to actually synthesize a frequency, a audio of a desired frequency is called direct digital synthesis. I'm going to talk through that algorithm on Monday. So we're going to revisit this example on Monday and talk about the algorithm that it's implementing. What I'd like to talk about today is sort of the infrastructure that's being implemented here. And I might wave my hands a little bit about the algorithmic aspects, but we'll come back to it on Monday and talk about that, okay? So in order to do what I just said, set up this SPI connection and a timer interrupt, the first thing that we do is include a couple of libraries. We include some standard C libraries, stdio, standard IO, and math. And then we include a couple of SDK libraries. These are libraries from the C SDK for the RP2040. In particular, we include standardlib.h. This is one of those high-level libraries that includes a handful of the lower-level hardware interface libraries. So this allows for us to do things like it automatically sets up a UART channel so that we can call printfs and print things out to the serial terminal. The other thing that we do, which is new, as far it is different from the example last week, is we include an additional hardware interface library. Now you'll remember last week what I said was every time we include a C SDK library, we include it in our source file, and we also have to link it in the CMake file. Right? So let me just briefly show you the CMake file for this project. And you can see that it looks essentially the same as the one that we looked at last week. We named the executable. Last week we called the executable Blinky. This time we're calling it DAC test, because I was testing the DAC. We list out the sources that are going to be used in this project. Start with the executable name. We only have one source file in this particular project. The private here, incidentally, just indicates that this source file is local to this particular project. if this repository had another project that had its own source file that was also called DAC test, this private would keep CMake from getting confused about which of those source files to include in this project. So it's indicating that the scope of this is limited to this particular project. And then what I want to point out is in this target link libraries list of this list, the C SDK libraries that we're going to include in the project, you can see that we have the executable name, Pico standard lib, just like last week. And we've linked the SPI hardware interface library additionally. Okay, so this is just to remind you that every time you include an additional hardware interface library in your project, you have to link it in CMake. If you forget, and you will, you'll get an error that says something of the variety like, it's going to yell at you about some function that you're using from that interface library being undefined, or something like that. And that just lets you know, oh yeah, I forgot to tell CMake to go link this thing. Okay. So we include these libraries. The next thing that we do is declare a handful of, we pound define a few variables. In particular, we pound define something that we're going to call 232. We're associating that with that large number, which is equal to 2 to the 32 power. I'll just remind folks that these pound define, these macros, these are textual replacements that happen before compilation. So what this allows for us to do later on in the code is use 232 in place of that large number. And before the code's compiled, everywhere that 232 appears, it's going to go in and just replace that text with the text next to it, that big complicated number. The advantage of this is we don't, wherever we use that parameter in our code, we don't have to retype that number and inevitably make mistakes doing so. Right? Instead, we can just get it right once and then use the shorthand everywhere in the code. It makes the code a lot more readable. So we do a few of those. I'll talk about how exactly those are used when we talk about direct digital synthesis. This is associated with the direct digital synthesis algorithm. But pound define 2 to the 32, pound define something called FS, that's going to be our sample rate. And then we declare a couple of unsigned ints. Again, I'll talk through how these are used on Monday, but for now, we'll just satisfy ourselves with saying, okay, we're declaring some unsigned ints. People know what volatile means?
It would not be optimized every time it accesses it, because sometimes if you don't add that keyword, it would just like ignore, even though it might change.
Yes, yes. So what volatile is saying is every time you're telling the system that it should go retrieve the most updated value for that variable from memory every time it's used. So we want to tag anything that is updated asynchronously with the keyword volatile. So for example, variables that are updated in interrupt service routines, right? Perhaps your code in main is using this variable to do something. The interrupt service routine interrupts and modifies the value of that variable. When you come back to main, you want to make sure that you retrieve the most updated value of that variable from memory as opposed to using some sort of locally cached value. So you'll see volatile wherever you're updating things in interrupt service routines. And we'll see some other keywords, but I'll talk to them as we encounter them in later examples. We declare an unsigned short, a uint16. This is going to contain the data that we actually send to the DAC. The DAC, as we'll see in a moment, expects 16-bit transactions. So we're going to store that data in a 16-bit data type, a uint16. And we pound define a couple of other parameters. Again, I'll talk about these in a moment, but in short, this contains all of the data that we're going to send to the DAC. It's a 12-bit DAC. These bottom 12 bits, we're going to mask in the actual data that we're sending to the DAC, the value that we want for it to convert to an analog voltage. So you can put a number in these 12 bits between 0 and 2 to the 12th. If you put 0 in there, the DAC will output 0 volts. If you put 2 to the 12th in there, it will output 3.3 volts, the greatest voltage that it can. These top 4 bits, we can look at the data sheet in just a moment, but these are configuration bits for the DAC. So it's giving the DAC some information about what we would like for it to do with the data that we're sending it. So one of the, I can't remember precisely what each one does, but one of them indicates whether we want it to come out of channel A or channel B of the DAC. Another one sets the voltage range that we want for the DAC to output. And another one is a reset bit or something of that variety. We'll double check in the data sheet in just a moment. The next set here, we're pound defining some macros here so that we're associating names with particular numbers, and these numbers stand for GPIO ports. So we're saying that the MISO port for this SPI connection is going to be on GPIO 4, chip select is going to be on GPIO 5, clock 6, MOSI 7, and we're going to use SPI port 0. These numbers, if we were to look at the Pico data sheet, let's see, we can take a look at the Pico data sheet. This graphic is showing us which signals we can associate with which GPIO ports. So we're using SPI channel 0 in this example. So you can see that for SPI channel 0, we can associate the SPI channel 0 TX signal. This is one of the little annoyances of SPI in particular, is different manufacturers, different companies, they like to use different names for the signals that compose a SPI channel. So TX, transmit, in another data sheet, you might see that as MOSI, master out, slave in. You might alternatively see it as SDO, SPI data out. They all mean the same thing. Folks just like to use different names for these signals. I'm not sure why. In any case, so we're associating GPIO 5 with chip select, if I recall. Yeah, so we're associating MISO with GPIO 4. GPIO 4 gets MISO or RX, master in, slave out. GPIO 5 gets chip select. GPIO 6 gets S clock, and GPIO 7 gets MOSI. And by the way, an easy mistake to make, I've seen this mistake in lab a couple of times. Just remember that the GPIO number is different from the physical pin number. Right, so for instance, GPIO 5 is attached to physical pin number 7. So when you're wiring things up, just be cautious of that. So that, in any case, that's where those GPIO values come from. We pound define another parameter. We're going to store the amplitudes of one period of a sine wave in an array in order to do this direct digital synthesis algorithm that I'll talk about in a moment. And then, okay, we see some of the logical code here. And I want to jump down to main, and we'll start talking through this in main. The first thing that we do is call a C SDK function called stdio init_all. This does things like set up the default UART port on GPIO 0 and 1. And then it prints a greeting, hello DAC. If you want to observe this greeting, the way that you do so is in each of your kits, there's a USB to UART dongle. It's the blue USB port with the breakouts at the end. You'll notice, incidentally, that one of those broken out wires is red and that there's a piece of electrical tape on that particular one. That's because please don't plug that one into the Pico. That's a 5 volt. There's 5 volts on that, and you can hurt the Pico if you plug 5 volts into it. So I've put some tape on there just to discourage that. But in any case, one of those breakouts is black. That's ground. You plug that into ground. One of those is green, and one of those is white. And you plug those into the UART, RX, and TX pins, GPIOs 0 and 1. Which one goes to which, I can't remember. But I'll look it up. Or you can see which one works. You're not going to damage anything by testing that. So we set up stdio, which sets up a UART channel, print a greeting. And then the next thing that we do is call a couple of CSDK functions from the SPI hardware interface library. In particular, we call SPI init, which apparently takes 2 arguments, which we'll investigate in just a moment. And we call SPI set format, which configures that SPI channel. The SPI init function, we could go into the CSDK guide and look at this one. I want to do that for a different one. For this one, the 2 arguments that it's taking is, the first argument is which SPI channel we want to use. There are 2 SPI hardware, there are 2 SPI channels on the RP2040, and they have names. The CSDK calls them SPI 0 or SPI 1. We're indicating that we want to use SPI channel 0. Which, by the way, that's what the little 0 is indicating, that these can be mapped to SPI channel 0. You'll see that, for example, GPIO 8 on physical pin 11 can be mapped to SPI channel 1 RX. So you see pins that can be mapped to SPI 0 and pins that can be mapped to SPI 1. We're deciding which one we wanted to use. If we wanted to interface with the DAC through, say, this set of pins as opposed to this set of pins, why? I don't know. Maybe we want to use some of the other functionality that's possible for these pins. Maybe we want to use this I2C channel, which means we can't use it for SPI communication. Then instead of using SPI channel 0, we would use SPI channel 1, because that's the SPI channel that maps to the pins that we want to use. Okay. And then the other argument that this takes is the baud rate. How many bits per second are we going to send over this channel? We have this set to 20 million bits per second, 20 megahertz. Where would this number come from? How would we know what to put there?
The maximum is 100 for the board.
We would get this number from the data sheet for the device that we're trying to communicate with, right? So if we open up the data sheet for the DAC, which you're all doing in lab this week, you can scroll through and it'll tell you the max data rate at which you can communicate with that particular device. And for the DAC, it's 20 megahertz. So we just communicate with it as fast as we can. So we set this to 20 megahertz. If you were to set this higher, you might start to see errors in your transactions. You could set this lower and it would still work. It just, your transactions take more time, right? So we set it as fast as it can go.
Why are baud rates like weird numbers then? Like 94 fat, like they're not like.
So
if I find a baud number on my like Arduino, it's like a selection of strange.
Yeah, if you look at so this is the baud rate for SPI. I agree that if you look at, usually if you look at the baud rate for a UART channel, it's either 9600, 38400, 115200. There's like a list of them. Where those numbers came from, I don't know the history of. Do you know, Bruce?
They're based on how fast you could run a teletype in 1920. And that was 110 baud. They're all multiples of 110 baud.
Interesting.
1920.
So in any case, this initializes SPIO 0, and we're saying we're going to run SPIO 0 at 20 megahertz. The next SDK function here configures that channel. And as arguments, it takes the port that we're configuring, the number of bits per transaction. In this case, that's 16 bits per transaction. That, too, is a value that you get from the data sheet for the device that you're communicating with. The DAC expects 16-bit transactions. You may have some other sensor that expects 32-bit transactions, in which case that would be a 32. Maybe you have one that expects 8-bit transactions. So you have to read the data sheet for the device to figure out what to put there. And then we configure the channel. In particular, we configure the clock polarity, clock phase, and the order for this channel. And I want to just talk very briefly about how the SPI protocol works so that I can substantiate what these things actually mean. So how does SPI actually work? The way that two devices that are communicating over an SPI channel communicate is there is a shift register that lives on the main device or the master device, and there's a shift register that lives on the secondary device or the slave device. These two are connected. There are 3 wires that connect these devices. One is the MISO line, master in, slave out. The other is the MOSI line, master out, slave in. And then there's a clock line. There's actually a 4th one too, chip select, which indicates which device, which may be on an SPI bus we're communicating with. But these are the data lines that exist. What happens when a transaction occurs is the clock line starts sending out pulses, and synchronously with those pulses, the least significant bit in the shift register on the master device gets shifted into the least significant bit, or I guess, yeah, You know what I'm saying? It gets shifted into the shift register on the slave device or the secondary device. So in this case, for an 8-bit transaction, there would be 8 clock pulses, and this data would get click, 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 sent into the secondary device, and likewise, the data that lives in this shift register will get shifted into the main device. So you can see that this is a full duplex communication protocol, and in fact, it's necessarily full duplex. In order to receive data, you have to send data. Right? We shift data out of some register on what will for us be the RP2040 into some register on what will for us be the DAC. And as we shift data out, there is data appearing in a register on the RP2040. Now, in the case of the DAC, if you look at the pinout for the DAC, there actually isn't a MISO line because we don't care about any data coming back from the DAC. If we were to look at the data that's appearing in the shift register where we would expect to receive data from an SPI device that we're communicating with, we would find something there. It might be just garbage. It doesn't matter to us. We're not going to use it anyway. But there is something appearing. It's whatever happens to be on that pin that we've mapped to MISO. So the way that this works, to look at a timing diagram, the way that a transaction occurs is you may have one master device, say it's the RP2040, that's communicating with a handful of, there may be a handful of secondary devices that exist on this SPI bus. The way that we tell a particular device that we're talking to it and not to another one is by lowering the chip select line associated with that device. So chip select goes low, and then for an 8-bit transaction, that device, the device that we're communicating to, will expect to then see 8 pulses on the clock line. 1, 2, 3, 4, 5, 6, 7, 8 pulses. And for the configuration that I'm showing you here, it will check the value, check the voltage on the MOSI line, master out slave in line, when the clock is high. And then you can see that the data on that line changes when the, so what am I saying? Data is valid on rising edges, changing on falling edges. It's making some sense? So it's this S clock line that is synchronizing the communication between the master device, the RP2040, and the DAC. The DAC sees these clock pulses, and it knows that on rising edges, the data is valid. It won't check the data on the data lines on falling edges because it might be unstable. The voltage is changing. Well, what you can see is this suggests there are a couple of degrees of freedom here. So in particular, as I have this presently illustrated, this clock line is idle low, active high. So when transactions aren't occurring, the clock is low, and then during transactions, we pulse it high. And also you can see that in this configuration, the data is valid on rising edges and changing on falling edges. In that CSDK function that we were looking at that was setting a bunch of parameters associated with the SPI channel, it's those degrees of freedom, right? So you can configure the clock polarity. Is the clock idle low, active high, or idle high, active low? And the clock phase. Is the data valid on rising edges, or is the data valid on falling edges? In order to figure out which configurations you need to set, you find that information in the data sheet for the device that you're communicating with. I'll show you that in just a second for the DAC, right? Or 2 degrees of freedom, that means an exhaustive, there's only 4 options. You might also just try all 4. In this particular case, you're not going to hurt anything by getting it wrong. It's just that you won't get any valid data. So this is illustrating the 4 modes here. So this is showing you clock polarity 0, clock phase 0, which is to say idle low, active high, and data is valid on rising edges. We might alternatively have polarity 0, phase 1, clock is idle low, active high, data is valid on falling edges. Some devices are set up that way. Or we might have polarity 1, phase 1. The clock is idle high, active low, and the data is valid on rising edges. Or the final option. polarity 1, phase 0, idle high, active low, valid on falling edges. 4 options. In order to figure out which is the right option, you look at the data sheet. So for instance, for the DAC, here's the DAC. Here's the pinout that you all were looking at. So this is 3.3 volts. This is chip select. This is the SPI clock line. This is the MOSI line. There is no MISO line because we're not actually getting any data back from this thing. These are the 2 DAC outputs, and VSS is ground. But so how do we know which mode to use? We would scroll down in the data sheet until we find a timing diagram. Let's see, I think there's a better one down here. Oh, let's see. Oh, okay, let me pause on this for a moment. It expects 16-bit transactions, right? I was mentioning that the bottom 12 bits are data and the top 4 bits are configuration. This is showing you what each of those 16 bits represents. So this is data 11 through 0, so that's the 12 bits of data. And then you can see that if we scroll down just a little bit, bit 15, the most significant bit, is indicating whether we're communicating. We want this voltage to appear on the A output or the B output. Bit 14 is a don't care. Bit 13 is a gain selection bit. And bit 12 is a shutdown. Okay, but this is what I was looking for. So what this is showing us is the timing diagram that this particular DAC is expecting. And what it's actually showing is that for this device, it will accept either mode 00, which what we just talked about was what that means is the clock is idle low, active high, data is valid on rising edges, or mode 11, the clock is idle high, active low, and the data is valid on rising edges. It will actually work with either. So if we look back at the code, we are configuring this such that we have 16-bit transactions, the polarity is 0, the phase is 0, the order, you actually can't change that parameter. That is indicating whether you want to send it out most significant bit first or least significant bit first. If you read the data sheet, that's not actually, as I read the data sheet, that's not actually something that you can change. It is what it is, but it's still an argument. I don't know why. Okay, so that's us setting up the SPI channel. We then need to map GPIO ports to that SPI channel, because you'll remember from the pinout diagram, we could map the chip select for SPI 0 to GPIO 5, but we could alternatively map it to GPIO 17. We could route that signal to either one of those GPIO ports. We have to tell the system which one we want to use. So that's what we do in this next series of function calls, where we're calling GPIO set function, which does exactly what the name suggests. We provide it with the GPIO port that we're configuring. Remember that these are from those pound defines up above. And we are associating a function, in this case SPI, to that particular GPIO port. For those GPIO ports, for example, GPIO 5, we're mapping GPIO 5 to its chip select function. If we used a different second argument to that function we were just looking at, we could have alternatively mapped it to the clock line for I2C channel 0 or the RX line for UART channel 1. But we're telling the system map GPIO 5 to chip select for SPI 0. And the same for the other ones. We're mapping the clock line to its SPI function, the MOSI line to its SPI function, and the chip select line to the SPI function. We then populate that sign table array. I'm going to talk about that in detail next time. For now, just suffice to say that this is an array of ints, and we're filling it up with ints. And I'll talk about how exactly that array is used next time, but that's just some C. Okay, and then we set up this repeating timer structure. And this is the next thing that I really want to pause on. what I want to talk about is, as I mentioned, what we're doing is working our way through the hardware in the RP2040, sort of one or two peripherals at a time. So a couple lectures ago, we did a tour of sort of all the stuff that's in here. And today, what we're spending some time talking about is the SPI peripheral and this timer peripheral. The timer peripheral, it's a good one to start with, I think, because in comparison to a lot of the other ones, it's simple. That is to say, there aren't that many registers that control and configure it. And people have different strategies for learning a new microcontroller. It's often the case as far as the folks that I've talked to about such things. Usually what people do is get an LED to blink, and then often the next task is figure out the timer and get a timer interrupt to run. It's usually just kind of the next thing that you figure out. So it seemed like the right thing to talk about. And I want to talk about this by looking at the data sheet. Let's look at the data sheet. There are, so let's see, we can go down to the table of contents and take a look at the timer, which is here. Okay. So the timer peripheral in this device is actually kind of unique as far as devices that I've worked with. The way that this is set up is there is, inside at the lowest level, there's a piece of hardware in the RP2040 that is ticking at once per microsecond. So there's a 64-bit timer inside the RP2040. 64 bits. All the registers are only 32 bits. How does that work? Well, the most significant 32 of those 64 bits are in one register. The least significant 32 of those 64 bits are in another register. And once per microsecond, every microsecond, the value increments by 1. Right? So it's counting up by 1 once per microsecond from boot up. Ticking once per microsecond, 64 bits. When is this going to overflow? I think it's something like 500,000 years. I think it's something like that. So if your code is relying on the fact that this timer, this whole 64-bit timer, is monotonically increasing from the time that you boot it up, that's a pretty safe assumption, right? It's probably something else is going to go wrong before that timer overflows. What is an application where you would care? The only one I can think of, I want to hear your idea in a second. Maybe you're like sending a small spacecraft to the nearest star system and you want to include information about when it was sent. It's going to take a long time to get there. If you're storing that information in the value of this 64-bit timer, maybe it shows up and it will have just overflowed like a week ago and they're like, oh my God, they're here. But that's the only example I can think of where you might actually care.
So sometimes we might want to set an NTP, manually set the clock so that it can be used for, like, for example, SSL certification.
Okay, sure.
So, what if I wanted to time out the half-life of some radio?
Okay, sure, maybe. But actually, the overflow that you might care about is the bottom 32 of those 64 bits will overflow every like 72 minutes or so. So there is if you're trying to set up some sort of interrupt event over lengths of time that are longer than 72-ish minutes, there's a separate peripheral available in the RP2040, the real-time clock. And you should probably use that one instead of this one. Okay. But what this is telling us is there's a single 64-bit counter, increments once per microsecond. We can read that time whenever we want to. And then associated with this hardware peripheral, there are 4 registers. Those registers are called alarm 0, alarm 1, alarm 2, and alarm 3. What we can do, the lowest level interface to this peripheral is we can write a value, a 32-bit value, to any of those alarm registers, alarm 0, alarm 1, alarm 2, and alarm 3. And when there's a match between the value in that register and the lower 32 of bits of the 64-bit timer, an interrupt will be thrown. So there are 4, let's just take a look quickly at the interrupt section. Remember how I said sometimes these things are coupled? So let's just look very briefly at the interrupts. I mentioned last time or a couple times ago, there are 26 interrupts that are shared between the two processors. They are given here. Okay, so what I'm referring to are interrupts 0, 1, 2, and 3. You can see they have names: timer interrupt 0, timer interrupt 1, timer interrupt 2, and timer interrupt 3. These are associated with those alarm registers in the timer peripheral. So if you write, some value to the alarm 0 register, then when that value matches the lower 32 bits of the 64-bit timer, this interrupt fires, and you can write an interrupt service routine associated with that interrupt. And if we go back to the timers section that we were considering, what we'll find down here just a little bit. Incidentally, before I go on, this is not the only timing resource on the RP2040. It's the simplest, I think, and it's the one that we're going to use in Lab 1. But the PWM peripheral has its own set of timers for configuring period and duty cycle and such. The PIO state machines can be configured to be timers, and you can configure them to increment at full CPU rate. The DMA channel has, or the DMA peripheral has its own set of pacing timers, and the ARMs themselves have timers. But what I wanted to show you was down here in the data sheet, there is an example of doing what I was just suggesting, which is doing setting up one of these alarms to fire an interrupt by manipulating those alarm registers directly. Right, so there's an example of how you might do that by going in and actually touching the alarm registers, setting a value there, and then writing an interrupt service routine associated with that particular interrupt. So if you wanted to interact with the timer at this low level, you could do that. What I talked about last time is what the SDK does basically is abstract some of this low-level functionality into function calls. So the folks at Raspberry Pi recognized that people would probably want to do stuff like this a lot. So in the SDK, they created a, let's see here. In the SDK, if we go to the hardware interface library for the timer, what we'll find is a bunch of low-level functions that automate those register manipulations. So if you want to do the register manipulations yourself, there's an example in the data sheet that shows how you might do that. This hardware interface library to the timer allows for you to do the same thing, but by calling these functions as opposed to going in and touching those registers yourself. Now, what might you do with a capability like this? So the fundamental capability here is you write a value to one of those alarm registers, and when there's a match, that interrupt fires. And it won't necessarily fire again unless you rewrite the value in the alarm register. Otherwise, it just goes off once, right? So you could, if you wanted to, in the interrupt service routine associated with that alarm register, rewrite the value in the alarm register to be equal to the current time as you measure from the onboard timer plus the same amount of delay, and then it would interrupt again when there was another match, right? So you could set up for yourself the logic that allows for you to set up a repeating timer interrupt. And the way that you would do it is set up an alarm to go off sometime into the future. When it goes off, rewrite the register to go off again the same amount of time in the future, and then it would keep going off. This too, the Raspberry Pi company recognized that this is something that folks are probably going to want to do. Set up a repeating timer interrupt. It's a pretty common thing that you do in a real-time application. So they have put together a higher level SDK library called Pico Time, Pico Sync, Pico Time. So I mentioned that what these higher level libraries do is they bring in the low level hardware interface libraries and add some additional logic to them that give you some of these capabilities, these higher level capabilities that you might want to implement. Things like a repeating timer. So in particular, this higher level library allows for you to implement timestamps It implements a sleep function so that you can do a blocking sleep for a while. It implements alarms and alarm pools. I'll talk about that in a second. And these repeating timers. An alarm pool. So there's levels of abstraction here. What the alarm pool allows for you to do is to associate a bunch of different callback functions with a single one of those low-level hardware timer interrupts. My model for this, and from the documentation, I can't tell if this model is technically correct or if it's just a model. My model for the way that these alarm pools work is very similar to the way that you might set up GPIO interrupts on a different microcontroller, where the way that the way that GPIOs are often arranged is into banks. There's a certain set of GPIOs associated with GPIO bank A or 0 or whatever the convention is for that microcontroller. And you configure it such that when there is a rising edge on one of the pins in that bank, the interrupt associated with that GPIO bank fires. And then if you want to take different actions based on which particular of the GPIO ports fired, it's up to you to then, in that interrupt service routine, read in the value of the GPIO ports, see which is the one that either went high or went low or toggled or whatever it was, and then call the associated callback function for that particular pin. These alarm pools are set up kind of similar, where you can associate up to 16 alarms with a single low-level timer interrupt. So what happens is each of those alarms has an associated delay. When there's a match between any of the alarm delays and the lower 32 bits of the 64-bit timer, a match between any of them, then the low-level timer interrupt fires. And then behind the scenes, the SDK is disambiguating to figure out, okay, which of the alarms in the alarm pool actually caused this to happen. And it calls the callback function associated with that particular alarm. So what's nice about this is you can set up a whole bunch of different callbacks, all using the same low-level hardware, right? So you're not consuming a whole bunch of your timers. You can associate a lot of stuff with the same timer. The cost of it is it takes you a little bit longer to get into the callback function than it does to get directly into the interrupt service routine. And then these repeating timers are one level of abstraction even higher, where the alarms, they schedule functions for future execution, schedule it to execute, 10 seconds in the future, and then it executes 10 seconds in the future. This allows for you to set things up such that some function executes every 10 seconds, or in our case for lab 1, at 40 kilohertz, 40,000 times a second. So let me just reiterate once more these levels of abstraction with the timer. At the lowest level, there's a 64-bit incrementing timer. It just ticks away. Associated with that timer peripheral are 4 registers, alarm 0, 1, 2, and 3. You write a value to any one of those registers, and when there's a match between that register value and the lower 32 bits of the 64-bit timer, the associated interrupt for that alarm register fires. The SDK abstracts that low-level capability of being able to write to the alarm register to schedule execution for some function in an interrupt service routine in the hardware interface library to the timer. That's your lowest level interface to the timer that isn't writing registers directly by yourself, right? That allows for, it is a series of functions that abstracts the manipulation of those registers directly. Now you could, if you wanted to, with that capability, you could implement logic that writes to the alarm register and then in the associated interrupt service routine, rewrites the alarm register to schedule execution repeatedly. Raspberry Pi company, again, recognize that this is something that folks are going to want to do. So that capability, too, is included in the SDK. It's included not in the low-level hardware interface library because it's not a low-level hardware interface capability. It's a slightly higher level one. There's logic surrounding what's going on there. So that capability is included in the Pico time high-level library, and in particular, in these repeating timers. Let's look at this in code. So what we declare is we create a repeating timer an object of type repeating timer, and then we call add repeating timer microseconds minus 25. The minus 25 here means that we want to call this function. We want for there to be 25 microseconds between function calls. If this were a positive 25, then the function would get called again 25 seconds after it terminated. If that makes sense. So this is indicating every 25 microseconds we want to enter the callback function. We're specifying the name of the callback function here. Null. Can't remember. I have to look at the SDK. I can't remember what this is. And this is indicating the timer struct here. And that repeating timer callback function, if we take a look at it, this is the function that's going to get called at 40 kilohertz. 40,000 times a second, this function will get called. The algorithm, these two lines are the direct digital synthesis algorithm that I'm going to talk about on Monday. But in short, what it's doing is computing the voltage that we want to send to the DAC, doing an SPI transaction to the DAC, and then it exits. And 1/40,000th of a second later, it re-enters this, computes a new voltage, sends it to the DAC, exits. The consequence of this is at a very regular interval, 40,000 times a second, we're sending new voltages to the DAC. In this particular example, that's producing a sine wave of how many hertz? I can't remember. I think it's 800. 800 hertz. We'll talk about this line of code next time too, but this is synthesizing an 800 hertz wave.
In this case, do you have to guarantee that the ISR takes less than like 1/40,000th of a second to complete?
Yeah. Okay, that is all I have for today. Question?
What happens if it takes more than 1/40,000th?
What happens if it takes more? I have to do this experiment. I think you exit and re-enter repeatedly. Bruce, do you know?
I've done that experiment by accident, and it freezes the CPU because it tries to make an interrupt.
Okay. See Friday people soon. See the rest of you on Monday.